last talk of this wonderful workshop. And it's a pleasure to have Ines Aniceto. She will tell us about algebraic study of
structure. An algebraic study, sorry, yes. So I think I'm going to follow the general idea of today and not really talk about gauge theories. Although, first, sorry, I should thank the speakers, and we will thank the speakers at the end. Or maybe actually, can we, for people who are leaving, can we thank the speakers for this, again, wonderful workshop for one more time? Thank you. So now you're free to leave and go swim if you want. So this idea came about, so I've been studying a lot of different problems. In fact, a fair amount of them linear problems, meaning I'm very interested in some cases of boundary value problems with some h bar, an h like a Schrödinger-like equation. But there's a whole range in applied mathematics as well and many in physics of problems which are singularly perturbed problems. So problems that you can have an equation. Imagine your variable is z, but you also have a bunch of parameters, and some of those parameters can be taken as h bar small. And if they come in the right place in the equation, that means that you have a singularly perturbed problem. So by the way, this is work with the SAM crew, which we're trying to now just finish off all the typos, which are plenty. So if there's typos in the talk, you just have to wait for the paper. So yes, asymptotic analysis, either in our variable z or in our parameter, can tell us a lot about the analytic structure. Even though we try to solve some of these equations perturbatively, if we try to understand beyond just the original asymptotic series and we try to understand what non-perturbative phenomena we have, then there's techniques that we can use to try and rearrange these perturbative and non-perturbative objects together to try and understand boundary value problems, some boundary layers, initial value problems. But more specifically, for example, for tau functions, we can use them to calculate where the zeros of the tau functions, predict where the range of the zeros of the tau functions are. That would kind of give you a glimpse on some certain types of phase transitions. Why does this happen? Because we have a perturbative series, we have non-perturbative terms, which typically are exponentially small. Think of it as instant-on corrections in some way. And but these, if you go in parameter space, especially if you're not doing the variable of the equation, you're doing a parameter, these can actually suddenly become large. B of order 1 actually dominate the system. And that means that you have a whole different physics happening in those regions. And you could think, oh, but my analysis is very local and very specific for a particular region where I can do perturbation theory. But the main idea is that if you actually have a complete, even if it's a formal solution, but it's complete, which is called the Tron series, you can do a lot and actually understand the regimes that are very far away from that very local area that you expanded in. So this is just the general idea. But what I will want to do now is that if I do have a parameter, that means that some very strange things. So if I'm doing a singularly perturbed problem and I'm doing an asymptotics in a parameter of phase space, some very strange things can happen to my non-perturbative terms. And what I'm going to do is focus on a very special class of cases where I'm going to define my Borel transform can be represented by an algebraic curve. And because we have the algebraic curve, we can actually interpret a lot of things that people see in these n-order linear ODEs singularly perturbed, but from a very simple perspective of analytic continuation. So what I'm saying is, like, I have an asymptotic, so I have an asymptotic observable. And I'm assuming that it's asymptotic, meaning it's factorial divergent. So I have and I have a parameter, like I'll have an ODE in Z, and I have a parameter epsilon, which you can think of h bar. And I'm assuming that I am expanding in small h bar. Maybe I should use, sorry, I'm not going to change variables. I should have used the h bar, but that's not going to happen because I'll swap to epsilon at some point. So I'm assuming that I have an expansion, but because I have the variable Z, these coefficients will all depend on Z. What is my Borel transform? My Borel transform, I define it as the Borel transform of Y in a variable omega, or W, sorry, which now I will basically from now on write it as phi of, sorry, ZW. Sorry, I'm just writing it several of the things. So I have a phi n of Z, W to the n, and where my, phi n of Z are just the original y n's of Z divided by gamma of n plus 1. If you want to think, this is, for whoever doesn't know, it's like if you were doing an inverse Laplace transform to each coefficient in the series. And the idea is that if you can, this now is a finite radius of convergence series. And if you can analytically continue it and understand it as a function with singularities, you can then do a Laplace transform, and that would be the physical observable that you're actually calculating. You had a question? No. Okay. So just to say, then what I'm saying is that then I can write, this is just so the result for the series is just it is didn't I say that it was
Laplace?
Did I say the Laplace transform? I am so sorry.
They are very close, but
No. This is the Borel transform. What I said is that I am very sorry if I said that. It wasn't meant to. This is the Borel transform, and what I meant to say is that this can be seen as doing an inverse Laplace transform to each coefficient. I am extremely sorry. It wasn't even on my radar, not on purpose. So, meaning I can write it, I can define a resummed, what I was saying, resummed series, now in Z in epsilon again, which is then, like I said, so this is just to have just some basic definitions. So, and when I'm doing this, of course, I'm not talking about seeing this from the point of view of a series anymore. I'm seeing this as in the point of view of a finite radius of convergence function with some singularities. So there's something that's, meaning when you're doing the asymptotics in Z, we talk about changing the contour of integration to find, and when you change the contour of integration, you can find some singularities, and that's what leads to Stokes phenomenon. Here, I am not going to do that. I'm going to take the opposite perspective, which is I'll keep that contour of integration, but my coefficients depend on Z. My singularities in the polar plane will depend on Z. So changing Z in CZ, what will happen is that there will be points at which the singularities will cross that contour of integration. And that leads to Stokes phenomenon. And what is Stokes phenomenon is just, what happens is that when any singularity of this function crosses the line of integration, you will have extra contributions, exponentially suppressed because of this exponential, which needs to be taken into account in order for you to continue to analytically continue your function in Z. That's the non-perturbative solutions that you find. So So if we have this type of thing, that means that just assuming that we have a series and doing that integration is not enough to express our observable. What we need is what is called the trans series. And the trans series, what I mean is really just that I include not only my perturbative series, but I include all possible exponential corrections that can show up from this Stokes phenomenon with some coefficients. Those coefficients, we need to fix them at some point by boundary conditions, by initial conditions, but then they're allowed to change when we have Stokes phenomenon. So now, so this is the trans series. I will put an explicit thing. So I want to put it to look back at where this is coming from. And of course, this is coming from the realm of ODEs. And when I'm talking about realm of ODEs, I'm talking about ODEs of this type. I equals 0 to n, p I z epsilon, sorry. So this can have, I'll ignore that, it could also depend on epsilon. So I'm taking that, I'm making some assumptions, which is the Pn of z, I'm taking it to be 1. So if it wasn't, I just divide by whatever it needs so that it's 1, the leading contribution. It can have higher powers of P, and of course for this, for everything to work perfectly as an algebraic curve, I'm going to assume that P is in fact a polynomial in Z and epsilon. And I will fix it to actually be just a polynomial in Z. So solutions for this is a formal trans series. So the trans series will look as Z epsilon So I'm just writing a formal solution. I can just plug in each one of these sectors with some exponential chi, including chi equals 0. In fact, because I'm assuming non-homogeneous equations, the chi equals 0 will be a solution. It will have to be part of the solution. And the sigmas, which can depend on epsilon, like I said, they're originally defined in some line by some initial condition or boundary condition. But when we have Stokes phenomena, they will be allowed to change by an exponentially small term, then it's the term that is multiplying the parameter sigma. So, so what I was saying, so y0, yeah. So sigma, in fact, sigma 0 and y0 are completely defined by the particular solution to this ODE, by the R. There's nothing there, there's no parameter. But I wanted to, so because we're not doing this asymptotics in Z, and we're doing it in epsilon, then if I fix the sigmas to be something, and then I tell you, but I want to change sigma to a completely different function of sigma, it's still a solution. What does this mean in terms of actually solving for the coefficients of these functions, of these expansions? Is that they will obey an infinite set of recursive ODEs, which means that for each one of the y case, or this case, for each one of these, you will have a new integration constant, and you will have an infinite set of integration constants. So then the question is, how can I actually, is there an unambiguous definition of these? Because if I can multiply any function of epsilon and still obtain a solution, then how do I define my trans series properly in the parameter h bar? Yet another thing is that there's equations for chi, but they're also not completely defined. They're defined, meaning the examples that I'll give, they define, it's a differential, algebraic differential equation for the chi-i's, which means that you actually have an equation for the derivative of the chi-i. So they're defined up to zeros. obviously, the 0 when chi could be included in this, but that's yet another ambiguity. So, what the hell? I'm trying to solve this particularly, but I don't have a way of defining anything in any particular way. So, this is why what I would really like to do now is, so I would like to hopefully convince you that there is a procedure to actually completely and ambiguously define this problem. And what does that mean? For example, when I was talking about Stokes phenomenon, I was saying that the sigmas can jump. Depending on how I define the y's, I will have that the sigmas can jump by a function of epsilon as well, which is extremely hard again. And that can be an asymptotic function of epsilon. The problem becomes more complicated. We started with something that was linear. So I don't want that. So what I want is to find a way in the Borel plane to have a natural analytic continuation from the original germ, whatever that is, such that when I deal with Stokes phenomena, these parameters can only jump by a constant. And that constant can be calculated. And this is when I turn to algebraic curves. And now let me stop with this, and we go back to the algebraic curve, and then I'll do basically the map of these two. Because we're in the realm of linear ODEs, I have a finite set of singularities on the plane. And some cases, and we actually have a way of finding examples that obey this. There's cases of ODEs whose Borel transform will obey, meaning the ODE is equivalent to a Borel PDE, linear PDE, and it's cases where the Borel transform will actually obey an algebraic curve. So what I want to then see is like to find a phi b such that is an analytic continuation of my germ, which means my Borel, I deleted the Borel transform, but the Borel transform associated to an expansion there. Such that basically if I define some curve that is defined in W phi b WZ, such that W is so what I want, this is an algebraic curve that is the locus, the zero locus of a Z-dependent polynomial. So what I want is to be, I'll have a polynomial such that Pz phi is 0. So polynomial in Z and phi. So I will assume that the curve is single valued in Z. Doesn't have to be, but it's much easier if it is. And we'll also define a projection from the curve to CW, which basically can be branched and can have, meaning it's the pre-image can have poles. An example of things like this that I will think of is something like that. So I have here my origin. So this is W equals 0 in some way and then I have branch cuts, but I can also have poles, which will be only on a single sheet. And of course, they will project to CW in particular points. what is the interesting thing here is that meaning as I move Z, a lot of things can happen here, which means that basically things that can happen, singularities can coalesce into a single point, or the projection of those singularities can coalesce without the singularities coalescing. So an example of that is that when you can have something like that, this could at some point become something like that. And that means, so this is also the zero. Why am I writing the zero? Is just because I'm doing, in fact, because of non-homogeneous cases, the zero is a special point. Meaning if I was doing homogeneous ODEs, this would not be the case. I would have, meaning there would be no choice of zero in particular unless you had some particular reason like an initial condition. So this is when the chi1, chi2, this is some chi3. This is when chi1, so this is for another z, this is chi1 equals to chi2, and it also agrees in the projection. And then, of course, I can have a situation where basically chi3 and chi2, chi1, so where the projection of chi2 is equal to the projection of chi3, and so chi1, this is the projection of chi1, etc. But you can see that in this case, actually in the curve, the two singularities do not match. Why does this matter? Because in fact, this is what happens, because in one case, you will have Stokes phenomenon. In the other case, you won't have the start of Stokes phenomenon at that point. So these are basically what we call turning points, when the chi's come together, coalesce. But some of them will be real turning points, and the other ones can be virtual turning points. And virtual turning points is when the projection actually is the same, but the 2 points in the curve are not the same. So, as an example, and this is a very simple example, I'm going to write a curve given by the polynomial where I have that chi1 equals z squared over 2, chi2 equals z minus 1/2. Again, there's reasons why I'm choosing these values, is because I know the ODE that this corresponds to, and it's a simple ODE. So this obviously double-sheeted surface, right? By the way, I'm not claiming that a lot of the work on the curve part is completely trivial. The only thing that is non-trivial here is the interpretation in terms of higher order Stokes phenomenon. So I have here chi1. Again, I have the chi0, which is a regular point, in fact, but because of the ODE, coming from the ODE, we care about it. And then there's a chi2, which is a pole. So things that are important in this case, the singularity structure. There's two types of singularity structure that are important here. The singularity structure in the curve, so which I'm going to call so this is the singularity which is Borel singularities. And I'm going to write this as gamma W of Z, which exists in the curve. And these are basically going to be all the branch points and poles corresponding to the the curve. And I also have, of course, the corresponding projection with pi of the Borel singularities, which I'm going to call the hat, which is the projection of. So and these are the branch points and the possible poles that we have. But we also here have the physical singularities. And what do I mean by physical singularities? Is that so I have all these singularities. If I do expansions, I have singular expansions of this curve around the points, the Borel singularities. What I have is that if I expand around those, the coefficients of such singular expansions can have singularities themselves in Z. And those are the ones that basically are going to be governed by the coalescing of different singularities. So what I wanted to write now is the physical singularities. And I think from that point, I go more to the. So I also write like the physical singularities, which basically for each chi, basically so if I choose a chi in the Borel plane from the Borel plane singularities, I have a singular germ expansion, which will look like, so I can plug it into the curve, and it will look something like W minus chi to some minus alpha. This is typically rational. Of course, if it's a pole, it's not rational. It's just a single point. And so that's my singular. And what I'm saying is that these can have singularities themselves. And that's basically this one is basically the singularities of the phi case of Z. So for my example that I was writing, I can actually explicitly invert the curve. I have 2 omega minus chi 2. Now I have 1 plus square root By the way, I am not stating what is the denomination here, because what I'm assuming is that if I define my germ at 0, meaning it will by itself define a particular denomination at chi 1, for example. So I will know. So this plus just means that there's a square root, and the sign of the square root will be defined by specific analytic continuation for a particular value of Z. So obviously, so omega equals chi 1 is a branch point. Omega equals chi 2 is a pole, which only exists on one of the sheets. So basically, this will define for me the gamma W, and I will also include the gamma 0 because, like I said, it's an important point. For my inhomogeneous ODE. But what I wanted to show you is that I can actually calculate by recursion the coefficients phi's, and what happens is that the phi k's at chi equals 0, so one of them, will go as z minus k. They'll have other parts, but the point being is, like, we have an exact expression, but the point being is that the coefficients go as z to the 1 over z to the k, so they have a singularity at z equals 0. And that means that gamma z of 0 is just 0. And also, if I did for around the chi1, we have, I mean, this one is a simple calculation as well. I can write 2 to the k divided by square root of pi. And now I have z minus 1 to the minus 2k minus 1, which means that the gamma z at chi1 is 1. And the chi2, by the way, the gamma z of chi2 is 0 because there's no singularities, there's no coefficients. As I mentioned, sorry, no. Indeed. Otherwise, it would be a serious problem, yes. So, final definitions, I promise, is turning points. So I've already said what are turning points. Turning points are the points where two of the singular points in our curve, in the gamma w, come together. But then there's virtual turning points, where two of these points in the projection come together. And obviously not all not all virtual turning points are turning points, exactly because we have a sheeted surface. So, sorry, I just said this, but yeah, I have. It's ij is a turning point. So a zij turning point if chi I minus chi j at zij is 0. And it's a virtual turning point if pi of chi I of zij minus pi of chi j zij is equal to 0. So a turning point, unlike the virtual turning points, of course, a turning point is points where my germ expansion will start becoming of smaller and smaller radius of convergence, because the radius of convergence is defined by the distance to the closest singularity. So that's what happens, in fact, when a turning point coalesces, when two singularities coalesce. So now I want to make the link, finally, to the ODEs and what can we see about this with the very slowly building up to the higher order Stokes. So remember that I had an equation, let me write it as a differential operator, which was epsilon n d dz n plus epsilon n minus 1 p n minus 1, let's assume it as of z, d n minus 1 dz n minus 1 plus p0. And what I had is that p acting on my y was my epsilon r, which was a non-homogeneous term. So this actually can be written directly for the Borel transform as a Borel PDE. And it's exactly equivalent. And what you find is that in the variable zw, what you have is dn dzn plus pn minus 1 dn minus 1 dzn minus 1 ddw plus so this is my now by Borel PDE. I can use one or the other to try and solve the things. And of course, what we have in terms of algebraic curve is that, so if this is my PD, I have that this operator, this acting on my algebraic curve is 0, but I also have that my polynomial that I had in terms, sorry that I'm using too many p's, acting on my polynomial phi and w was 0. So this determines for me the algebraic curve. This tells me that the same algebraic curve obeys a Borel PD. As I mentioned, in fact, it looks like there's not many cases where this is true, but you can construct cases. You assume a particular order ODE. You can't a priori know what is going to be the rank of the algebraic curve, because meaning the two things are not meaning it's the rank of the ODE and the algebraic curve. The order of the algebraic curve is not, they're not directly linked, but you can basically construct examples of ODEs that obey algebraic curves and vice versa. And just to say that our example is, let me just again, for the example that I was giving, I did have a different example, but I think that I'll skip because no time. So our example, the equation is epsilon square alpha prime plus epsilon 1 plus z 1 prime plus z y equals minus epsilon. The example that I gave of that algebraic curve is just this ODE. And this is the other example, which I'm going to ignore. And so now I go really to Stokes phenomenon. And what we want is, of course, it's not enough to know the algebraic curve in the Borel plane. To know the y, I need to know the contour and the weight that I give to each contour, to each sector in the sorry, to each sector in the trans series. So what I need is to actually define my observable. So my summed observable needs the curve, but also needs a contour choice, which is going to be basically a sum of, so if I have D sectors, I will need to have at least, a Hankel contour for each one of the chi-i's with some weight. That is the one that is given by initial conditions, but it's the one that when we do Stokes phenomena is allowed to jump. So this is the parameters of the trans series, where these are Hankel contours. What does it look in the curve? It looks like choosing contours, and like I said, I have the chi0 because it's on non-homogeneous contours around each one of the singularities. One of them will have a branch cut. So this defines for us the inverse Borel transform, and the question is now, what happens when we change z? So from this point of view, when does Stokes phenomena happen? It happens when basically you vary z and the chi-i's enter the contour of a chi-j. So basically when you're starting to move and there's a shift in that one contour crosses the other contour, you'll have Stokes phenomena. You'll need to take it, and the sigmas will jump by some value. So what we say is that when that happens, if chi I enters the contour of chi j, so what happens is if chi I enters the contour of chi j, you say that basically j switches I, and the c chi I will go to some c chi I plus some s, which is the Stokes constant. And lines, so now lines Lij in Z, where this happens, are basically Stokes lines. So you're going to have a collection of Stokes lines, but then you also have naive Stokes lines, which is basically what the typical definition of a Stokes line would be. Oops. Which is, so the usual naive, let me call it this one, Stokes lines, will be defined by Lij, such that the real part of the projection of chi I is greater than the real part of the projection of chi j, when the imaginary part chi I projection as well, chi j. So what happened with the naive Stokes lines is that, why am I calling them naive? Because there will be situations where you think that a singularity is crossing your path, but what you find is that it's just not on that sheet. So in the projection, it's really crossing the path, but in the actual algebraic curve, you see that it's not. And the example of that is, for example, so I have here my chi1, my chi2, and this is chi0 in the different sheet. So my contour of chi0 and basically chi2 is crossing, but it's actually not here in this line. Or I could have chi2 not on this line for a different z. Chi2 will be here, chi0, chi1. And basically, when chi2 crosses the contour of chi1, it actually goes. The thing is that if I project to CW, what I have is like some chi1, chi0 with a contour, and chi2 crossing the contour. I don't see the difference. This is higher order Stokes. This is what happens when people talk about higher order Stokes phenomena from the point of view of an algebraic curve. And this is something that can happen. It won't happen in second order linear ODEs homogeneous, but can happen on any higher order or non-homogeneous cases. So let me just see. So exactly. So from the point of view of the naive case, this is indistinguishable. But if you go to the actual point of view of the algebraic curve, it's very clear where the difference is. So for my example, I can write to you, so Z01 equals 0. These are the turning points, by the way. And this means that 0 can turn on 1. Here it's Z12, which is at 1. And then there's a virtual turning point, which is z hat 0, 2 equals a half. And what happens here is that, what lines do you have? You have a Stokes line, 1 turns on 2. You have another Stokes line here, which is 0 turns on 1. But then you have a truncated Stokes line, which would start, you'd think it starts at the turning point here, which is L 0 turns on 2. But basically, it will only start here because chi1 will block it appearing from before. And basically here is where you'd expect the naive Stokes line to start, but it doesn't. And you can define this by, is there any color I didn't use? The yellow. By what is called a higher order Stokes line, which is defined by the locus, where basically, so it's when the argument of chi2 equals to the argument of chi1. Why? Because this is exactly the point at which one of them crosses the path of the other. So just this is the general idea of what happens in the Stokes phenomenon, the fact that you can see higher order Stokes phenomenon just from the fact that you have an algebraic curve. But then I go back to the original question of, I told you that if I was just doing things from the point of view of ODEs, I had a whole bunch of ambiguities. Meaning, I can tell you how, meaning, if I have an algebraic curve, of course, I can try and map to algebraic curve, which gives me the natural analytic continuation of my Borel transform. But I would like to be able to do that even if I didn't know the natural, if I didn't know the algebraic curve. And this is what I now go back to finish very quickly. Which is in some way, I would say it's the trans-series approach. So and I'm going to just do it for my example. Meaning it's the same thing, it doesn't matter, but for my example, I have y of z epsilon equals my particular solution, completely fixed. And then I have a parameter e to the minus chi1 over epsilon y1 plus chi2 sigma 2 e to the minus chi2 over epsilon y2. But here are the ambiguities. I only know chi1 prime to be z, and I only know chi2 prime to be 1. Moreover, I have differential equations, a whole set of differential equations for yk, which so they're first order. Which basically, for each k, I introduce a new constant, integration constant. And just to tell you like what it looks like if I wanted to solve for the y1, I can rewrite things like sum k equals 0 to infinity. There's ck, these are the integration constants. I'm writing k minus a half. The minus half is convenience. And then I have sum L equals 0 to infinity, minus 2 to the L, epsilon to the L plus a half, gamma of L plus a half, divided by square root of pi 1 minus z. Why am I writing this? Not because of anything, because I actually wrote this expression before. These were the coefficients that I found from the analytic curve at chi1. But here, they don't show up with the analytic curve. And you can massage them into this where you have a whole function, right? S of epsilon that I don't know times something that that is absolutely fixed and actually agrees with the algebraic curve. So in this case, analytic continuation means that S of epsilon is trivial, it's 1. But again, if I had what if the algebraic curve told me that I wanted to calculate that it wasn't exactly this, that it was something else? Actually, there's a way of comparing this with any analytic continuation of the Borel transform, and it's by knowing just that the resummation of S of epsilon times Y of epsilon Z is equal to integral from 0 to infinity dw minus epsilon Borel transform of epsilon convoluted with the phi b. So if you now compare this with my analytic continuation in the Borel plane, I can actually obtain the coefficients of the S that I need, such that I obtain from here the natural analytic continuation. But again, I'm saying this if I have the algebraic curve. So how do you actually do if you do not have the algebraic curve? You can do better. And the way you can do is actually you compare the expansion of the two germs at the point that they're coalescing. If you know that they coalesce at some point, then you can compare the direct analytic. I'm 10 minutes, right? Yeah. You can compare the analytic continuations of those two germs. You have two germs in the Borel plane. They're expanded at chi1 and at chi2, but they coalesce at some point Z star. What you can do is change variables to what's called the inner variables. It's like, basically, it's like defining this as my new epsilon, or 1 over epsilon, chi1 minus chi2 over epsilon as a new variable that then you can take to 0 in some way. So you define the new, what you do is like you go to inner variables and you still have these two expansions, but then you change the order of the expansions because you can also expand them around the coalescence point, the turning point. And if you do that, you change the order of the two, you now have a whole string. I'll write a couple of equations, but you have a whole string of resurgence problems in some sense, but where you have a singularity always at the same point in the Borel plane, which is, let's put it, W equals 1. But a whole expansion around the coalescence point. And that allows you to actually compare the two expansions directly via Darbo's theorem. And that will give you exactly the natural analytic continuation at chi2 coming from chi1. So that's the general picture. So let me just write this more explicitly. This is germ matching. So I have a germ chi1, which has a turning point chi2 connecting it to some different germ chi2. And we write it like that. So that point is the coalescence point between the two. And if I do this, and okay, just to keep in mind, why do I care about this? Because if I do the proper, I don't want to say proper, sorry, but the natural analytic continuation, I know that the Stokes phenomena is going to only have constants when I analyze it. It won't have functions of epsilon. So I know that my Borel transforms at I, 1 or 2, it doesn't matter, are going to be singular at chi I, so with some rational number, and then they will have some phi 0 I, these are coefficients of Z, plus W minus chi I phi 1 of I of z plus etc. And of course, what I said is that I have chi2 minus chi1 at z star is 0. So they coalesce at that point. We'll further assume that the coefficients can have singularities at z minus z star. They will have. We know for a fact that at least one of them will have singularities at z star, but actually both of them can. So what we'll assume is that the coefficients phi and I can have singularities at that point, which is going to be some gamma I. And in fact, for n, you can see that even if they start at n equals 0, that they'll start growing. And when I write here, it's the worst growth possible. Many problems will not exactly go like this, will be more tame, but I am writing the worst possible scenario in some way. What you're going to get in some cases is that you get a bunch of zeros. So what you do then, you change to inner variables. What are the inner variables? The inner variable is a variable defined by S, which you define omega minus chi1 divided by chi2 minus chi1. Basically, I'm putting this at S equals 0, and then I will change these coefficients with because these depend on Z, right? So all of these depend on Z. But this, so chi1 will be at 0, but chi2 will be at S minus 1. So I'm putting everything at S minus 1, at 0 or S minus 1. So if I do that, so what I have is phi 1, sorry, I wrote it as phi 1, where I'll transform, is going to be S minus alpha 1, and then I'm going to have phi 0, 1 of Z plus S phi 1, 1 of Z plus etc. And the same thing for the phi B of 2. Now it's going to be S minus 1 minus alpha 2, phi 2, 0 of Z plus S minus 1, phi 1, 2 of Z. So these phi's, the reason why they're not the same as the phi's is because they will include some powers of this chi I minus chi j. You can calculate them exactly, but it's not the thing. And of course, these phi n's will have a singular behavior at Z star, which is going to go by as minus gamma I minus some alpha I beta. And what I said is that now you exchange expansions in S and S minus 1 with expansions in Z minus Z star. And if I expand, so around Z minus equals to Z star, what I have is that I can just write the phi n i's as Z minus Z star minus gamma I minus n, alpha I beta. And then I'm going to get a whole bunch of coefficients here. Psi 0, 0, just one second. Psi I 0, So again, I'm changing the variables from S to S star. And what I then do is basically, if I do for n equals 0, n equals 1, so if I have here 0, 0, I have 0, I will have the same things for psi 1, 0, I, etc. And what I find is that now I can go through these directions, and basically using Darbo's theorem, I can get the coefficients order by order in Z minus Z star related to the previous order. So with this, I can go from phi 2 to phi 1. Like I said, meaning there's formulas for this. You can actually make this precise, but they're not very illuminating. But all of these are resurgent problems, each one of them at the S minus 1. And so where can we go from here? This allows us to do analytic continuation, allows us to understand Stokes phenomenon in higher orders. Meaning algebraic curves are really neat because we can really see the algebraic picture of all this. There's plenty, so there's physics situations where instead of 1z, you have z1, z2, much more complicated. So you have an algebraic curve with the two moduli. But we have actually one problem like that. So what is the relation to the large Z asymptotics? Is there a possibility of a case where you have an algebraic curve on both cases? This we don't know. And of course, how it relates to how you would impose boundary value problems, for example, on this as well, is a question, is an open question. And well, the goal, non-linear problems, but that's, even though some of these parts could work with non-linear problems, of course, the algebraic curve, you'd have to have an infinite sheeted algebraic curve, which is not really, at the moment, doable. Anyway, so thank you.
Any questions? In the beginning of the talk, you were mentioning the perspective application to the analysis of the evolution of the zeros of tau functions.
No, what I, sorry, what? No, what I said, no, not, I wish this. No. What I meant is, like, if you do have a Tran series and you actually analyze the exponential parts, right? If you have the knowledge of the exponential parts of the Tran series of a tau function, of, think of Palinvest 1 or any of the Palinvest, for example, you can use that to predict the distribution of zeros of truncated solutions, for example, or meaning I've been doing work with the special functions of solutions of Palinvest 2, and you can really see the distribution depending on which tau n function you're talking about, the distribution of zeros growing with n. So, and all this from just understanding properly the non-perturbative terms that come to the Tran series. So that's what I meant. I meant that even though this is a very perturbative, looks like a very perturbative approach, it actually has analytic information in it. That's what I meant.
You start with a series expansion in epsilon, right? And then you construct Tran series which are like e to some function of x. Now there is a particular context in quantitative theory, which is the one of the large charge expansion, where people claim to have series expansion in 1 over n, but then non-perturbative effect of that e to the minus square root of n. Do you know any simple examples where this type of things happen?
I didn't say anything like this, but so the 1 over n that you have expansions in square root of n resembles a lot of having a gs squared expansion where you actually some of the exponentials are in gs. But apart from that, this kind of, but but I think that's not where the question is heading to. The question is the fact that you actually have, if you do the analysis in Z, in this very dumb, simple example, you have expansions in 1 over Z squared, but one of the exponentials is Z. So this is not a Gevrey 1 class. So what happens in these situations is that you can still analyze this, but you're beyond the class of Gevrey 1 functions. And worst thing is when you have mixes of it, when you would have square root of n and n. Then it really becomes basically a zoo of things. I'm not sure if that's what.
No, I think I forgot. I don't remember the correct powers.
But I think, meaning the point being is that actually this does happen. Meaning the fact that you can have examples with where actually you have several powers even in the exponential, and that's and like I said, but you're starting going beyond the realm of everyone functions. You can still do things, but it's not as a trivial thing.
Any other questions? If not, let's thank Ines again.
And
Also, I suggest to thank our valuable organizers,
Again.
Julia, Alessandra, and Pasha. Thank you very much. And we hope to see each other in 1 year more. Yeah,
with a shower.
Very high hopes for Julia, those guys, we should leave it here.